We return to our stack of crates being pulled by the gator, and I'd like to look at a few ways this could play out, with particular attention to that force of friction between the two crates, that internal force of friction seen in this pair of forces here and here. Now, in our first scenario, let's suppose both crates are moving as one across the floor. So the gator's pulling in such a way that this crate and that crate are both moving together to the right. If that's happening, we can see that there will be a force of kinetic friction between crate B and the floor. Let's look at that force of kinetic friction. We pull out our usual formula for calculating it, but note that now in this scenario, since there are multiple surfaces, we should be specific and say that the force of kinetic friction at surface 2 depends on the coefficient of kinetic friction at surface 2 times the normal force at surface 2. So mu k2 times Fnb. What I'm saying is this force of friction here depends on the normal force also there at that surface. It has nothing to do with this contact force up here. That's a different surface, so that would be a different friction. All right, we've already got this expression here for the normal force at the ground. So putting this together, we have our expression for force of friction at surface 2. All right, we could find the acceleration of our system using step 1 of our usual process. So finding the external forces to sum. Between our two free body diagrams, the only x direction external forces are these two, that tension and force of friction 2. So there's our sum of external forces. We could substitute this in for friction 2, and so we have this as our expression for the acceleration of the system. Now, I want to look at that internal force of friction under these conditions. This force of friction right here that is pushing the top crate along with the bottom crate, helping it keep up. Now, if the crates are sticking together, then that must be a force of static friction, a traction helping the top crate grip onto the bottom crate. So how big is this force of static friction right here? You might be tempted to answer that question by jumping right to a formula like this. Friction is fun, but recall that this formula doesn't refer to the force of static friction always. That gives you the maximum force of static friction. And we don't necessarily know that that static friction is maxed out right now. This force of static friction here could be any size it needs to be to keep the two crates together, to prevent them from slipping apart. It's acting to oppose slippage. So we don't know how big that force of static friction is, but we can find it by going to our usual step 2. Let's just jump to N2L for the top crate to find that internal force. So here we go. N2L for the top crate. The only horizontal force acting on it is that internal force of friction, FF1, right here. And we can find its size by rearranging here and then substituting this expression in for that acceleration since they're moving as one. That's how we would find the size of that force of static friction keeping the top crate moving along. And we can see that the harder the gator pulls, the bigger this tension, the bigger the acceleration will be, and thus the bigger that force of static friction would have to be. So it'll be as big as it needs to be to make the accelerations match. Now, I'd like to notice here that there's a possibility that these two forces here could cancel out. If the gator gets the crates moving and then sort of lets the tension decrease a bit in the rope, this tension could drop such that it matches FF2 and these cancel. So there's a possibility that tension is equal to that force of kinetic friction with the ground, in which case the acceleration would disappear and we would be under equilibrium conditions here, in particular a dynamic equilibrium. And if the crates are not accelerating, then that force of static friction between the two crates would also disappear. This force right here would disappear if we're in dynamic equilibrium. Note that if this force doesn't disappear, there's nothing here to oppose it, so the top crate is guaranteed to accelerate if this force doesn't, is present. So if these two are balanced, then our situation looks a bit like this. Those two would be balancing So no acceleration for the crates. We've been in dynamic equilibrium. There's no friction necessary here. Both crates would just be cruising along at a constant velocity. There's no force necessary here to keep this crate moving once it has gotten moving if they're going at a constant velocity. They would just be drifting along here. A second possibility I'd like to consider is, regarding that force of static friction right here. We know it can be as big as it needs to be to keep the crates from slipping, but there is a maximum value. It can be as big as it needs to be up to a point, and this tells us the maximum value that static friction can have right here. So what if the gator pulls so hard that he maxes out static friction? So if static friction is maxed out, now our sort of algebraic logic is slightly different because our internal force is known. That force of static friction can now be calculated from this formula. So let's try that. Going to Newton's second law for the top crate, if we have the maximum value of the force of static friction, that's going to tell us the maximum acceleration that the top crate can have without slipping. So let's find FF1 max. That's this formula, but that force of static friction max at surface 1 depends on the coefficient of static friction at surface 1 times the normal force at surface 1. So the max value of static friction here depends on the contact force here at that same surface. These forces are linked. This force of static friction max value does not depend on this normal force down here. Those are different surfaces, different forces of friction. So what we want is mu ks1 times FAB right here. So, mu s1 times FAB. And we already know the size of FAB. We worked that out earlier. That's MAG. So note how the masses cancel, and this expression here tells you the max acceleration that the top crate can have without slipping. Note a couple interesting things, like mass canceled out, so the max acceleration that that crate can have doesn't depend on how big the crate is, just on what the material is. So now, knowing the max acceleration that the top crate can have without slipping, we can sort of reverse our usual two-step process. We found the internal force. Now we can go backwards to find the acceleration of the system. Or actually, to find that, knowing this acceleration here, we can plug that into N2L for the whole system. So here's our system N2L here, just rewritten. And if I know what the max acceleration is, that tells us the max tension in that cord. So we could solve this potentially to find the maximum tension in that cable. So this is helping us determine how hard the gator could pull without breaking static friction. Okay, we've come a long way here, but we've got another scenario to consider. So if you like, pause the video for a moment, take a breather, look back over this, and make sure you can reconstruct the arguments and the analysis that we've just been through. And when you're ready, let's go on to our second scenario. What if the gator does indeed pull hard enough that the bottom crate slips out from underneath the top crate? What if he pulls harder than that maximum value of tension, breaking static friction right here, so the two crates start to move no longer as one. If the bottom crate slips out from underneath the top crate, then they're not moving as one anymore. They will have different accelerations. So if that tension is great enough to break static friction between the crates, then there will be kinetic friction at surface 1. If the two are slipping on each other, moving with different accelerations, that slippage at the surface of contact between them, that'll be a kinetic friction right there. So FF1, this friction here, becomes kinetic, and so we find it by doing mu k1 times this FAB right here. Mu k1 times FAB, we know the size of FAB, so there's our force of kinetic friction once slippage has occurred. And noting that they no longer have the same accelerations, we can see it illustrated here. So if here's one moment and here are the crates are a short time later, we can see that if they have these three different accelerations, then crate B will have moved farther than crate A in that time. And the center of mass, that imaginary point in between the centers of mass of the two blocks, that imaginary center of mass for the system, that has also accelerated and is at a different location. So we have three different accelerations we could potentially find. Let's do so. Okay, starting with the acceleration of the top crate, we'll do N2L for just the top crate. Only force accelerating it forward is this one, which is that kinetic friction, as the bottom crate sort of drags the top crate along with it. Because kinetic friction doesn't oppose motion, it opposes slippage. So that slipping here will sort of drag the top crate along with the bottom crate. This determines what the acceleration will result. So here is that expression for the kinetic friction between the two. That'll give us this acceleration. Note again how the mass cancels out. This is the acceleration the top crate is guaranteed to have once it's slipping. No matter how hard the gator is pulling or what the mass of the top crate is, this is guaranteed to be the acceleration of that top crate once slippage has occurred. Now, Newton's second law for the bottom crate. We can go back to our free body diagram. Now we need to sum all three of these horizontal forces to find the acceleration of the bottom crate. We already have expressions for the force of kinetic friction between the crates, that's this, and the force of kinetic friction between the bottom crate and the ground, that's this. Oh no. Sorry, the force of kinetic friction between the crates, that's this, and the force of kinetic friction between the bottom crate and the ground, that's this. Okay, lastly, let's find that acceleration of the center of mass, of that imaginary point that's moving along with our system. For that, we just sum the external forces, which we've done before. We know these are the only two external forces here. So there we would have it, the acceleration of that imaginary point, the center of mass. And I suppose now that we've come this far, we have the accelerations of the two blocks and the acceleration of that imaginary point in between them. We could take this opportunity to verify the definition of the acceleration of the center of mass. It's that weighted average of the accelerations of the objects in the system. So that ACM can be found by taking the weighted average of these two accelerations here. You see in the picture how the acceleration of the center of mass has a value in between those two values. So let's look at this weighted average idea, returning to that. Mass A times acceleration of A, let's see, mass A times acceleration of A, that would just be FF1. And mass B times acceleration of B, mass B times acceleration of B, would be this sum of terms right here. So this numerator is FF1 plus this sum of terms. We see how FF1, that internal force, would cancel out. And so that canceling, we can verify that using the strict definition of center of mass acceleration, we get the same result as we do from the systems version of Newton's second law. Those two are in agreement with each other. Well done.